Hi guys, welcome to classification processes. This is part 8, or it's part 3, or looking at sampling. And there is going to be a bit of an overlap continuing with some of the things we're looking at. Last lesson you would have looked at surveying techniques, so you would have gone through quadrats, transects, pitfalls, mark recapture, and hopefully have an understanding what are some of the advantages and what are some of the disadvantages. In today's lesson, our goal is going to be looking at these two down here, okay? So these two down here. So looking at minimizing bias, and they give you a couple of things that they want you to be able to look at. So size and number of samples, random number generators, counting criteria, calibrating equipment, and noting associated precision. So you should, guys, get a table or something down that you're going to write individual information about each of those points there. And the last thing we'll go through is methods of data presentation and analysis. Alright, so to begin with, minimizing bias. As with all sampling techniques, stratified sampling has a certain degree of error. However, we can reduce the amount of bias in a number of ways. So let's go through those different ways there. Get this table in your book. They're the ones they want you to look at and go through how bias is actually reduced. So to begin with, a series of replicated measurements should be taken to work out the mean of the characteristic being studied and to ensure an estimate is reliable. So what do I mean by that? Well, if I was doing an area, I don't do one quadrat. I would do several quadrats. I would even, if time permitted, do several different transects across an area potentially, okay? And that way you've got an ability to calculate a mean. It all depends on what you're looking at and your time in your zone. If, for example, you're going just across the sand dune and you only had time just to do one lot, well, that would be fine. If time permitting, obviously you need to be able to do more. If you're doing quadrats of an area, random quadrats, well, you need several. And I taught you last lesson how you can calculate how many you need. A single measurement is generally insufficient for conclusions to be drawn about the characteristic. So by doing more quadrats, you're able to more effectively calculate a mean, identify outliers, collect more reliable results, and also to be able to draw effective conclusions about the characteristic you're studying. If you don't, well, those things, they don't apply there. So quadrats also need to be large enough. So the number we've talked about, now we need to consider the size of the quadrats. So they need to be large enough to be representative of the community, but not so large as it takes a very long time. So think about the area you studied. Was it a forest? Was a 5 by 5 large enough? Was it a rocky shore? Did you go 2 by 2, or would a 1 by 1 have worked more effectively? So sometimes quadrats can be too large, or sometimes they're not large enough for the particular zone. So it's important that you use and can comment on the effectiveness of the size of the quadrat. And this is something that you would be, if you're doing your student experiment and you use quadrats, you're going through these things when you're looking at reliability and validity. So the number of quadrats from each stratum should also be proportional to the relative size of the habitat. And I've mentioned that so many times in stratified sampling, but it is a key idea and something that could easily come up in an exam, okay? So you need to make sure that the number of quadrats you use is representative to the relative size of each habitat you looked at. And that's an important thing, again, when considering the number of quadrats that you're using. Random number generators, well, they're another way that you can reduce bias. So random number generators should be used to determine the position of quadrats within each stratum. As we said, you can set up your different areas, okay? You might have a transect, or you might have a different area like that, and you use a random number generator to know where to either place a quadrat or where to place your transect, okay? So you're going to start your transect here and follow a particular gradient as you go along. You can have random number generators on your phone. Easy thing to keep with you and have in the field there. If you're unable to have access to a phone, well, maybe set up the area beforehand and already do your random number generator on the computer or something before you go into the field. But obviously by using a random number generator, you are not selecting the location where you're going to measure, and that's going to help minimize or reduce the bias in your results. So random number generated sampling should be used to avoid bias in data, as we can see here. Now this one uses numbers and a letter. You can get random number or random letter generators, and these are basically showing where to put the quadrat as you go. So sampling should be representative of the whole population, and as a result of hopefully using these things, that can actually happen. Obviously we did talk about with random sampling, that sometimes you're not going to be able to cover a gradient, and therefore quadrats and things like that might not be the most effective. You might do a belt transect, which would still have quadrats there, but a way that you can more effectively look at the gradient in the environment. Strict counting criteria also needs to be applied and followed, i.e. what constitutes an individual in ground cover plants, or how much of a plant must be within the quadrat to count it. So before you actually start, you need to have set out in your own mind, in your group's mind, what counting criteria are we going to do. Say, for example, here you're counting some of these mussels on the rocky shore, and you have a mussel that's just slightly in here. Are you going to count that, or does it need to be a whole mussel? Do you see, by having a strict counting criteria, it can help eliminate bias? If you went into another area and you had very little, but you had one guy there and you're like, oh, I want to count that, but here with so many, it's like, oh, I'm not going to count that because I've already got so many in there. By having the strict counting criteria, it will minimize your bias. Same with plants. If I'm doing a 10 by 10 meter, does a branch over my quadrat count as that plant being in there, or does their trunk physically have to be in that quadrat? With ground cover, okay, if I have part of it in there, so just a branch, again, am I counting that ground cover as being in my quadrat, or do I need the actual base of that plant to be there? Whatever you do, you need strict counting criteria, and it has to be followed consistently throughout. Again, these are things that you can say that if you did, you're adding to the reliability, and you can use them in your reports to help justify how you ensured your results were reliable and accurate. And if you've already done your student experiment and you hadn't followed these, well, these are things that you would talk about to improve the experiment next time you did it. Calibrating equipment and noting associated precision. So calibrating equipment improves the accuracy of the device. So basically, it's getting the device back to being an accurate level. Say with scales at the shops, you're hoping that they're calibrated so they're not out, and that's something that they should be doing time and time again. With you and your different meters and different devices, you should obviously have them calibrated before using them to ensure that the results they're giving you are actually accurate. So the more precise the equipment, the more precise and accurate the measurements will be. And this is when we come to noting the associated precision. Let's say, for example, you're using a test tube, okay, and it has some measurements along the side. Well, there may be a plus or minus 0.1 mil error margin on it. Or if you're using a thermometer, and of course you're using visual or your eyes or ruler, there may be, say, plus or minus 0.5 millimeters if you're using a ruler error on there. All different things. Scales could be plus or minus 0.01 grams or 0.1 grams. Whatever it might be, you should note the associated precision, because that is the source of error. Nothing is going to get it exact for some of these equipments we're using in high school. Even our 2-point scales, 2 decimal point scales, do have an error margin. You need to note what that error margin is, plus or minus whatever, and you would include that in your assignment as a potential source of error. Now, if you know that you used a measuring cylinder in, say, collecting some enzyme, or, for example, you used a graduated pipette, which has a lower error, they're things that you can talk about, okay? So if you initially use a measuring cylinder, you may say, to improve this, I would use a graduated pipette next time to collect more precise and accurate results, okay? They're things you do need to look at to help minimize bias. So ensure your equipment's calibrated. That could be something you improved if you know it wasn't calibrated initially. And also you could note your associated precision as a source of potential error. And you could look at what devices have the highest precision to help ensure that your results are accurate and reliable. So these are basically a summary there for you guys on how you can minimize your calibrating equipment. So go through, make sure you know those different techniques. So basically, it's not only important for external exam, but important for your assignments, because these are all scales at the shops out. You're hoping that they're calibrated validity, and also something when you're considering your improvements for your experiment. So when it comes to data presentation and analysis, there's a few things that you need to consider. Firstly, with presentation. So sample data can be presented in a number of ways. The simplest is in a table form. So when you go out to the field, you should have a table that you're going to put your data into. That can be your raw data table. You'll then generally add a process data table. From there, you'll then do your graphs. Now, it is much easier to see patterns and trends, because you do in student experiments actually have to analyze it and those trends and patterns in your data when you put it in a graphical format. All right, so that might be a column graph, or it might be a scatter graph or a line graph, depending on what you're doing. We'll be tending to go with those column graphs and those scatter graphs here in biology. Now, it is important to notice that when you are expressing your measured values, you can only use as many digits as you initially measured with your measuring tool. So if you had 1 decimal point from your measuring tool, do not, when you're doing your means and standard deviations, that start to have 2 decimal points. Use the amount of decimal points or numbers that you had from your original data. When looking at data presentation and analysis, there is this resource which is being provided by Dr. Gurian Ang. And if you have been around long enough, you will have encountered him. A fantastic guy, and he's prepared many great things. So you'll be able to hopefully get them from your teachers, or you can take a quick screenshot here to be able to use that. He has provided them for people, and it is a great resource. So full credit to him, and thank you for sharing that with all of us. Now, this infographic here shows us how we can look at data analysis and data presentation when dealing with the student experiment. And particularly here, the focus is if we've done some stratified sampling. So let's look at how it works through. So in the student experiment, you are going to begin with a research question. And you need to firstly determine, am I looking for either A, a difference between different groups, or B, a correlation between 2 variables that I'm focusing on. Now, I'm going to start with differences. And I actually think differences are a great way to go for your student experiment for a real clear-cut way of doing analysis and presentation. So the focus here is, are there differences in insect diversity between the sclerophyll forest, open rainforest, and closed rainforest? Now, I've got 3 different areas I'm looking for. Are there differences in the amount of insects? Very clear-cut differences. You would obviously do a pitfall trap, as we've talked about. You would do multiple pitfall traps there. Now, for differences, you might look at, is there a difference between the woodland colonizer and pioneer zone for the amount of tree species, or the amount of shrubs or ground cover? Okay, you might look at that. You might look at, is there a difference between the high tide or the low tide zone on the rocky shore? You may even make it simpler. Is there a difference between disturbed or undisturbed forest, or just simply an open and closed forest? Okay, so there are some great ways that you can get going with a student experiment. When you're going to analyze that data, what should you be doing if you're doing differences? Well, firstly, you'll tabulate your data. You will have a table, and you'll collect multiple repeats of those different quadrats. So you'll have multiple quadrats. From there, you will calculate a mean, standard deviation, and standard error in biology. So that's important to know when you're analyzing your data. You'll calculate those 3 things there, okay? So you obviously need those values, and you can use Excel, and hopefully you're skilled enough for that. If not, there's a student experiment video you can watch that will help you. The other thing that you need to be able to do is perform t-tests on these values, because we're looking for, is there a difference? Now, if we come down here and see some of these results, and we have 13 for closed rainforest, open rainforest, I'm going to go that as 7, and here I'm going to go that as 6. Now, those results are different, okay? We can see that those numbers are not the same. However, they might not be statistically significantly different. Why? Well, looking at this one, if I've got 13, that kind of goes up to 16. So my error margin for this might be 3, okay? My error margin for open rainforest, where we're going from 10 to 4, so we'll say 3 as well. And this one, we're going from 6 to 9, okay, down to, or are we down to, let's just say that's 3 for argument's sake. So we've got a standard error of 3 for all of them. Now, sometimes your standard error will be close. Sometimes it'll be very different depending on the results that you actually collected. Here, they're all the same, but do not expect them to all be the same ever. Now, what I'm actually looking at for these results, while my numbers are different, I have an error margin on it. And those error margins are basically telling me that if I was to do this experiment again, I would get a value of 13 plus or minus 3. So my true value that I would get would be between 16 here and 10. So that's what I actually have as a true value. Now you can see here for open rainforest, if I was to do it again, well, yes, my value is 7, but I have a plus or minus 3 error margin. So that means my result could be anywhere from 10 to down here 4. And you'll notice that, well, 10 and 10, they're actually the same. So what's that showing me is, in this experiment, if I was to do it again, even though I've got different numbers, I could actually still get the same result for those 2 forests. So there isn't actually a difference. Now, I don't analyze it by doing these numbers up here. I analyze it by using a t-test as a statistical way of showing this. So I'll perform a t-test in Excel from the values I have. Again, there's another video showing you how to do that. And I'll come up with what we call a p-value, which shows how statistically significant a result is. A great word to have to say. So if that p-value comes out at less than 0.05, you have a statistically significant difference. So you can say with certainty statistically that yes, there is a difference, say, between the amount of insects you find in a sclerophyll forest and a closed rainforest. I have my t-test to prove that, okay, my data value. However, if that number is greater than 0.05, well, you can't say that. So in that case, you would say there is no statistical significant difference. So there might not be a difference between the amount of insects in a sclerophyll and open rainforest. Even though this number is different, statistically though, there is no difference because of that error margin that you have associated with it. So when you are analyzing data for differences, so you need to understand this data analysis, you'll do two things. One, you'll calculate your mean, standard deviation, and standard error in a table format. Two, you will perform a t-test to calculate the statistical significant difference in your results. That's the way you'll analyze those results if you're looking for a difference. In data presentation, when you come down here, well, you are going to present differences as a column graph and have error bars on it. So one, when you're looking at a difference, you are going to use a column or bar graph, and two, you are going to add error bars to your bar graph. So think about when your research question is a difference, presentation, you have your table with mean, standard deviation, standard error, you perform a t-test, and down here you construct a column or bar graph that has error bars on it. That's how you will present that data. And those error bars, another way of looking at it, if there is an overlap between those error bars, well then we can see that those results are not statistically significantly different, but you should be performing a t-test as a better standard to show that difference. Just commenting on error bars not being different isn't good enough if you can perform a t-test on those. So you would end up performing 3 t-tests on this. You do a t-test to compare the sclerophyll and open, the sclerophyll and closed, the open and closed rainforest there. So you do 3 t-tests to show are those results actually different to one another. So that's if you're looking for a difference between the groups. I actually think that's a really good, easy way to go about it. However, if you are looking for a correlation between variables, so the example here is there a correlation between soluble fertilizer concentration and the growth rate of plants? Or if you're doing some field work, you might go, is there a correlation between distance from a disturbance and the diversity of plant species? Now, if you're doing something like that, you would need a very large area to be able to fully show some differences there. Other correlations, is there a correlation between the amount of organisms or the abundance of organisms or diversity of organisms from the low tide zone to the high tide zone on the rocky shore? So again, you're looking for this correlation of distance as you move along. Now you might have decided that you're going to look at that as simply just doing high tide and low tide. Is there a difference or is there a correlation? Now, depending on how you phrase that and word it, will determine on how you're going to present the data. So if you were doing a correlation, you'll still present, I should say, analyze the data in a similar way. You will have a mean, a standard deviation, and standard error. So that means you need to collect, again, multiple repeats of those quadrats or whatever it is so you can calculate those things. The key difference now, though, is you are going to construct a scatter plot. If it's a difference, we are doing here a bar or a column graph. Here we're now doing a scatter graph in Excel, okay? So you then need to ask yourself this question: is there a pattern you are expecting? If your answer is no, what you can simply do is fit your line or pattern the best fit as a trend line onto your data, okay? So the trend line against your means with errors, but do not obtain R-square values for means. So here, if I do not have the data I was expecting, I just fit my line or pattern of best fit as a trend line, and then I add my error bars. Now, when doing error bars here, you've obviously calculated your mean and you're presenting them. Why? Well, there is no actual pattern that I was expecting. So as a result, I just do my line of best fit, I do my error bars, and I graph my mean results, okay? So I do not obtain an R-square value from my means. And that's one of the key things. If I do this, I do not need to do an R-square value. Many teachers are obsessed with getting you to do an R-square value. If you've graphed your means, do not obtain an R-square value, okay? So here, if the data is what I expected, so it might have been a linear trend that the further away I went from a disturbance, I was expecting to get greater diversity. Or here, is there a correlation between soluble fertilizer concentration and the growth rate of plants? As the concentration of fertilizer increased, the growth rate of plants also increased, and it was a linear result. So if I was expecting that, or it might have been, in this case, a parabolic trend here, because the abiotic factor reaches an optimum, and then as I get even further, I add too much fertilizer concentration, it starts to inhibit that growth of those plants there. Okay, so if I now have a pattern that I was expected, all right, as my trend line, I add the trend line that I was expecting. So in this case, it might be a parabolic trend line, it might be linear, it might have been logarithmic, it might have been exponential. Okay, so I'm graphing here not my means, but you'll notice I'm graphing my raw data points. And that is the key point. I graph means if it is not the pattern I'm expecting. If it is the pattern I'm expecting, I'll graph my raw data points. I will add my trend line to that, and then I'll obtain R-squared values. So data as expected, I present it as a trend line. I use a line or scatter plot here, adding my trend line in, and I do obtain an R-squared value. Now remember, the higher that R-squared value is to 1, the closer it fits that particular trend. Do not say your results are more accurate or more reliable. It just means your results fit that trend better. Okay, so you do what we call a regression analysis. So perform regressions on raw data to determine the gradient and strength of the correlation by obtaining and interpreting R-squared values. Okay, so I might get a gradient if I've got, say, a linear graph. I can obtain my gradient so I can know the rate at which that is actually changing, and of course I do an R-squared value. Now that might be quite confusing, but just let's break it down. One quick summary here for data analysis and presentation. If I'm looking for a difference, say between different groups, data table, mean, standard deviation, standard error, I do a t-test. I present that data as a column graph or bar graph, and I add associated error bars to it. That's if it's a difference. If I'm looking for a relationship or correlation between two variables, so as this increases, this should happen here, okay? So I'm not just looking for a distinct difference, I'm looking, as this happens, what is happening to this other variable? Well, I once again, for data analysis, I do a table, I calculate mean, standard deviation, and standard error in biology. I then do a scatter plot, okay? If my data follows the expected trend, I do that scatter plot and I graph my means with error bar. If it doesn't follow a certain trend, I should say, I do my means and error bars on that. And I just add a line of best fit to it. However, if my data does follow the expected trend, well, what I do is I do a scatter plot, I add a trend line, and I do a regression analysis to show how closely that data actually did fit with that particular trend, okay? And I can also calculate a gradient from there as well. Hopefully those things make sense there. So from this video, guys, you should understand how to minimize bias. So know those different steps and techniques, and you should now have an understanding of how you can present or your data. So for us, we'll always be looking to present it as a graph. So you'll have a table and either a column graph if there's differences, or a scatter plot with a trend line there if it's a correlation. When it comes to analysis, if it's a difference, we'll have those same values, so mean, standard deviation, standard error, but we'll perform a t-test, and if it is a correlation that we're looking at, we will have, yes, again, that same mean, standard deviation, standard error, but we will perform a regression analysis instead of a t-test on those results. All right, guys, stay tuned for the very last step of these videos, which basically has some practice questions for you to look at.